Dear students, welcome to the next lecture of microcontrollers. So today we will start with the stack. So it's a special function register, and we will study what are the functions of this stack in today's lecture. In the previous section, if you recall, we discussed how a call instruction could implement the basic concept of a function or a subroutine. We will now see how this stack is used in the process. So the stack is a section of the built-in RAM. So if you recall, we had the built-in RAM, and then we had several special function registers within that built-in RAM. So stack is one of them, and it is used by the CPU to store information temporarily. So this information could be either data or a memory address, and the data itself is always from another register. Okay, so stack is really temporary in nature. So you push some information in the stack to save it temporarily, and then do something else, and then you can take back that information from the stack. So another register called the stack pointer is also there, which is associated with the stack. So this stack pointer registers, it points to the location of the stack. Okay, so the stack pointer register is 8 bits wide, and it is capable of taking values from 00 to FF. And when the 8051 is powered up, the stack pointer register by default contains the value 07. So see, it doesn't start from 00. The stack pointer starts from 07, and if you push some information on the stack, then the stack pointer increments. If you pop up some information from the stack, then the stack pointer decrements. Okay, so let's see what we mean by that. So as I was saying, we use this push instruction to store a register in the stack. Okay, and to retrieve this contents, we use the pop instruction. So as we push data onto the stack pointer is incremented by 1, and when the data is popped off the stack pointer is decremented by 1. So let's say your register 0 contains this information, so you use this instruction move R0 with this data. So R0 will contain this data, and now if you want to move the contents of R0 to the stack temporarily, then you use this instruction push 0. So this 0 indicates that it is in the register R0. Okay, and simply using this instruction will move the contents of R0 to the stack. Okay, now the question would be like which R0 we are choosing, because there are 4 register banks and there are 8 registers R0 to R7 in each of those register banks. So which register bank is chosen, that depend on these 2 bits that are there on your program status word register. Okay, so in your PSW you have these 2 bits. So if these 2 bits are 00, then register bank 0 is chosen. If this is 0 and 1, then register bank 1 is chosen. If this is 10, then register bank this is the MSB and this is the LSB. So if this is 01, then register bank 1 is chosen. If this is 10, then 2, and 11 means register bank 3 is chosen. So depending on these 2 bits, whichever register bank is active, that particular register bank's R0 will be pushed to the stack by this instruction. And similarly, by using pop1, let's say, you can pop the contents of the stack to register R1. So you only use these indices to denote which register you are operating with. Okay, so push and pop, these are the two instructions. If you use pop2, let's say here pop2, then the contents of the stack will be going to R2. Okay, and so on. So in the above program, the stack pointer is initially set at 07. Okay, you remember that while powering on, the stack pointer initially points to this. We just discussed in the previous slide. So when we push some information to the stack pointer, then the contents is stored at 0008. Okay, and the stack pointer is incremented by 1. Okay, so so yeah, so 0007 or 07 hex, whatever, this is the initial starting address of the stack. When you push something, then the contents is stored at 0008, the next location, and the stack pointer is incremented by 1, and hence the stack pointer is now locating at this address. So whatever the stack pointer is showing, so let's say this is your stack. Let's say this is your stack. This is the area of the RAM where your stack is there, and the stack pointer by default is initialized at this 0007, and this is the 0007 or the starting address of your stack. So whenever you push something, that moves here, which is 0008, and the stack pointer gets incremented, and this number is updated from 0007 to 0008. Okay, again, if you push another thing, then it moves in the above location in the stack 0009, let's say, and the stack pointer again gets incremented to 0009. Okay, and for pop operation, when you are bringing stuff out of the stack, the reverse occurs. Okay, and you note that the stack is a last in first out process. So whatever went last comes out first. So when you push something, whatever is here, the final contents, if you pop something, that will come out first. So last in first out. Okay, so let's see this example. So what is the value of R2 and the stack pointer register at the end of the following assembly program? So let's say you have your R0 contains this after you execute this instruction. Then the next instruction is moving this number to R1. Okay, so now you are doing push 0. Okay, so let's say your stack pointer is initialized at 0007. Okay, and let's say this is your stack. Okay, so when you are pushing the contents of R0, so let's say this is your stack. So at this location, which is 0008, you will have the contents of R0 because you are doing push 0. So let's say 0FEX, this is here, and the stack pointer will move or increment to 1 value. So now the stack pointer will be 0008. Now you do push 1. So push 1 will push the content of register 1 to the next location. Okay, so that will be 0009, and you have 10 hex here, and the stack pointer increments to 0009. Okay, now you're using pop2. Okay, so pop2 will move out this value because it is a LIFO, or last in first out. So whatever was last in here, that will go out when you do pop2, and this value 10 hex will now move to the register R2 because you are using pop2. So and since you are popping out a value, the stack pointer which was here now will decrement to one value, and the final value of the stack pointer will be 0008. Okay, so this is what we want. So what is the value of the R2? So R2 will have 10 hex, and the stack pointer register will finally have this 0008 or 08. So now let's see what's the role of the stack during the calls. So when you call a subroutine, let's say by lcall, the stack keeps track of where the program counter should return to after completing the subroutine. Okay. So to do this, the program memory location of the next instruction, which will be the current program counter value plus 3, is pushed onto the stack, and the stack pointer is incremented by 2. So so there are many things happening here. So first of all, when you are using lcall, okay, so whenever in your code you are using lcall, if you recall, lcall is a 3-byte instruction, right? So wherever in your program lcall is, the moment this is executed, it will jump to the address that is pointed by lcall. It will go to the subroutine address. But since lcall is a 3-byte instruction, the program counter will be incremented by 3, and whatever is that next line of the code, of the original code, that line will be the next instruction after the subroutine is finished. Okay, so that's why this value, whatever is this value program counter plus 3, is pushed onto the stack, and the stack pointer is incremented by 2. Why? Because the program counter requires 2 bytes to uniquely specify a location. Okay, and the lower byte is stored first, followed by the upper byte. So this is also important. Okay, because when the subroutine is finished, when it is returning to the main code, it will go to this line, whatever this line is, program counter plus 3. Okay, and that was pushed onto the stack. So stack is keeping a note, or it's kind of a lookup, okay, where the program needs to return. Okay, and the program needs to return to this address which is stored in the stack, and the lower byte is stored first. So since the stack is last in first out, okay, so the lower byte is stored first, followed by the upper byte. So it will read the upper byte first and then the lower byte, and together it will form the 16-bit address, which is program counter value plus 3, and it will return to that line of the original code. And for this reason, you must be very careful about modifying the contents of the stack during a subroutine. If there is an unequal number of push and pop instructions, the program counter may not return to the correct location following the return instruction. Okay, so let's look through an example. So let's say we have this code. The main code is like move A with this number, then move R1 with this, move the contents of A to R2, and then you call this subroutine. Okay, using the A call instruction, and then you are going to this first line of the subroutine. Okay, so let's see. So you are using A call instruction. So A call is a 2-byte instruction. First of all, so the program counter, which is locating to this line at the beginning of the A call instruction, will be containing this number. Okay, 00026. Now after the A call instruction is executed. Since it is a 2-byte instruction, the program counter will be now program counter plus 2. So that is this number. Okay. So after calling a call, it is going directly to this subroutine. But after finishing this subroutine, after this return instruction is executed, it will return to this line. Okay. So this line 0028, which is now PC plus 2, that has to be stored in the stack. Okay. So let's say your stack. Let's say this is my stack. So 0028 will be stored here. Okay. So the first byte goes here. So this is 28, and let's say this is 00. Okay. And let's imagine that this is my stack pointer, which was initially 0007. That is incremented 2 points, and it is 0009. Okay. So now let's see what's happened inside the subroutine. Okay. After this instruction, I have moved to the subroutine by saving the location of the next instruction in the main code here in the stack. Okay. So now I have moved here. In the very first line of the subroutine, I am using a push instruction. So whatever is within register 1 by this instruction, that value will be moved to the stack now. So now the stack is here. Okay. Stack pointer is locating to this address, which is 0009. Okay. So here the contents of register 1 will be moved, which is 01. Okay. So here we will have 01. Then we have another push. So now the contents of register 2 will move. So register 2 has this number, because we move this number to A, and then we move A to register 2. So after this instruction, we will have the stack pointer will locate here, because it will now increment to 000A. Okay, and it will point here, and here we will push this value 0A0. Okay. So now you are doing something else with registers R1 and R2. Okay, you are saving the contents of R1 and R2 in the stack. So see how the stack is used as a temporary storing place. And then you are doing something else with register R1 and R2. You are moving other values in R1 and other value in R2. You are using those values to add, and then you are popping the value of R2 back again. So whatever was pushed here, that value is returned back. So this value will, the 0A0 will now go back to register R2. Then again you use another pop instruction. So this value 01 will go back to register R1. Okay, and then you return. So when you return, your stack now contains, after these two values are popped back by these instructions, the stack pointer now indicates this location. Okay, and it will be at 0009. Okay. Okay. So this is the value which you are interested in when you are executing the return instruction, because this value will get you back to 0028, this line of the original code, which is just after the subroutine was called. Okay, and whatever this line says, it will follow this instruction. So see how important it is to balance out the number of push and pops inside the subroutine. If there is, like, let's say 2 pushes here and then 1 pop here, then the stack pointer will locate to this address. Okay, and while you are returning to the main program, the address of the line where it will return will be wrong, because it will just read the first two values instead of these two values. It will read these two values if there was a mismatch in the number of push and pop instruction. So this is something which you don't want. Okay, so this is our stack contents in the previous example which I walked you through. So it's showing in a more nice and clear way. So let's say again, let me reiterate the fact like how important it is to have equal number of pushes and pops within the subroutine. So if you have 2 pushes, the 2 pops will clear these 2 contents out of the stack. Okay, and the stack pointer will locate to this address, and when you are returning back, you know that these 2 makes the address of the line where you want to return. Okay, breadboard. But let's say if your push and pops are not balanced, let's say you have used two pushes, but then one pop is used by mistake and you forget to use another pop, then by mistake the microcontroller will read these two as the address of the next line of the main code. So instead of 0028, it will return to 0100. Okay, which is totally wrong. Okay, that is different location and everything will be messed up. So this is important to balance out the number of pushes and pops. All right. So remaining 8 are like crystal, ground, then you have 3CC, and there's some other things like AE, ESEN, and we will check, we will see the functionalities of all these things along with the all the IO ports. So let's see. So as I said, we have the following things: the IO IO ports, so your VCC, ground, crystal 1, crystal 2, reset, EM, PSEN, ALE, and so on. So let's go on to the functionalities of pins. So let's say we have VCC. VCC is E48 provides positive supply voltage, not helpful. Ground is E10, it provides ground supply voltage. Crystal 1 and crystal 2 together are used to hide the crystal oscillator that provides the clock frequency of the microcontroller. Okay. So they are connected like this, and they are pin 19 and 18. Now let us look on to the IO ports of the microcontroller. So in general, we have 32 IO ports. So there are actually 4 ports. Each of it has 8 pins. So there are total 32 IO pins. So this is P0 and the different 8 pins of P0 from P0.0 to 0.7. Then we have P1, here we have P2, the 8 pins of P2, and then here we have the 8 pins of P3. And then we can see there are some other pins, so it's a 40 pin device, and the remaining 8 pins are like VCC, then you have ground, you have PSEN, ALE, EA, and so on, and then you have the reset. So all these pins have their own functions, and we will discuss those now. So this slide actually summarizes what I just said about the pin structures. So you have, apart from the 4 ports and the 32 pins associated with those 4 ports, you have VCC, ground, crystal 1, crystal 2, reset, EA, PSEN, and ALE. So let's look into the functions of these. So VCC is the positive supply voltage, which is 5 volt, and it provides the energy or the power to make the microcontroller chip work. The GND is the ground pin, and this is always connected to the ground supply voltage, which is 0 volt. The crystal 1 and crystal 2 are arranged like this. So basically these 2 pins are used to connect a crystal oscillator that determines the clock frequency of the microcontroller chip. Then you have the reset pin. So when this reset pin, usually it is active high, so this means that during the normal operation it should be tied to low, okay, and if it is made high, then the device will reset, which means that all values stored in the RAM will be lost, the program counter will be reset to 0, and the CPU will fetch instruction at the starting location, which is 0000 hex of the memory. Then you have the external access pin, and this is usually active low. So when it is tied low, it indicates that the program code is stored in the external ROM. If it is tied high, it means that the internal ROM is used for storing the program code, okay. And this pin, external access, along with the PSEN, determines that whether you are using an external device or not, okay. So PSEN, as I was saying, this stands for program store enable, and this would normally be connected to the output enable pin of the external ROM, okay. So all these pins, this PSEN, then EA, etc., and this ALE also, these pins, they are used for interfacing an external device to the microcontroller, and you will be able to appreciate their functions more when we study specifically interfacing with external devices later in this module. So but just let's quickly go through the functions of them. Let's continue. So ALE, this stands for address latch enable, and this is a pin that is used for multiplexing or rather demultiplexing, actually both multiplexing and demultiplexing the port 2 of your microcontroller for addressing and data purposes, okay. So so basically in your microcontroller you have this 8051, and let's say when it is interfaced with an external ROM, then you have some data that is going to this ROM, and also you need to address this ROM. So your address bus needs to be also activated. So these when this happens, let's say this is done through the port 2 of your microcontroller 8051. Okay, and port 2 has 8 pins. Okay, so the lines that come out of this port 2, there are 8 lines out of it. Okay, and these 8 lines can be used to send data to the ROM. At the same time, these 8 lines can also be used for the lower half of the address. So if you want to address a location of this ROM, the addresses are 16 bits. Okay, so so when you have, let's say this is your ROM, and these are the different address locations. Each of these address location is 16 bit, but the data stored here is 8 bit. Okay, so so the 8 bit data comes out of port 2 of the 8051 and stored here. But when you are trying to locate the address of this data, this is 16 bits, and out of this 16 bits, the lower 8 bits are also identified by this port 2. Okay, and the higher 8 bits are identified by port 0. Sorry for the confusion. Port 0 is used for this functionality which I was just saying. So the data that comes out of the 8051, that comes through port 0 and is placed here in the ROM, but the address of the specific location, let's say, is determined by 16-bit address. So that 16-bit is determined by port 0 and port 2. Okay, so port 0 gives the lower 8 bits of the 16 bits, and port 2 gives the higher 8 bits of the 16 bits. Okay, and since port 0 is used both for data and address, okay, so there has to be a way to multiplex this or switch between data and address, and that is actually done by this ALE pin. So when ALE is equal to 0, data is being provided to port 0. When ALE is 1, an address is being sent out from port 0 to the external ROM. Okay, so we will study these in more detail and in more clearly when we study interfacing of the microcontroller with an external ROM. But now, just to give you an idea of the function that this ALE pin performs, I just tried to draw this and explain you. So basic concept is that port 0 is used both for addressing and for data, and to do that, to separate those two functions, you use the ALE pin. When ALE equal to 0, you use port 0 for data purposes, and when ALE equal to 1, you use port 0 for addressing purposes. So so as I was saying, let's move on to the functions of the ports now. So as I was saying, port 0, this can be used as a general purpose input output, as well as it can be used for multiplexing the ROM addressing bus, okay, with the data bus. So this multiplexing operation is taken care of by the ALE pin, whether it is 0 or 1. Depending on that, it will be either performing as a data bus or the address bus, the lower byte of the address bus. Okay. Port 1, again, this is just a general purpose input output port. It doesn't have any alternative function. Port 2, again, it can be used both as a general purpose input output, and also it is used as the higher byte of the addressing bus for a 16-bit external RAM block. Okay. And then port 3, this also has dual functionality, so it can be used as general purpose input output ports, but then it also has these functionalities. So for example, 3.0 and 3.1 is used for serial communication, for receiving data and transmitting data. 3.2 and 3.3 is used for external interrupts. 3.4 and 3.5 is used for timer operations, and 3.6 and 3.7 are used for writing and reading from the external memory. Okay, so you will again get to know the details of these pins when you study these topics later in this module. Okay, so when we study serial communication, we will get to know about what are the functions of these two pins in terms of receiving and transmitting data. When we study external interrupts, we will get to know what are the functions of these two pins in terms of these int 0 and int 1, and so on. Okay, so right now, just for your information, you try to appreciate that port 3 has the general purpose input output function as well as all these different functions. Okay, so you can see that all the ports except port 1, so port 1 is only for general purpose input output. The other ports has alternative functionalities. For example, port 0, this does general purpose input output as well as address and data multiplexing. Okay, then port 2, it does general purpose input output plus addressing. Okay, and port 3, as you can see from this slide, it does general purpose input output plus other functionalities, and the other functionalities are given by this table. Okay, so these are the functions of your ports. So now let's see, when you are using the ports for general purpose input and output, how to write to a port and how to read from a port. So writing to a port is simple. You just move some number to the port. Okay, so let's say the following code sends a binary equivalent of this to port 1. Okay, so to do that, you can move the number 55 hex, which exactly reads in binary like this: 01010101 to accumulator, and then from accumulator to port 1, or alternatively you can directly move this number to port 1. So this is writing, as simple as that. Let's say if you want to read from the port, then you have to do an additional step. So you have to configure the port for reading, and to do that you must first write ones to all port bits. So this step is necessary. you have to write 0FF hex, which means all ones, to all the 8 pins of the port. So you can move this FF to A and then from A to port 1, or just directly you can move this number to port 1, and in that way you configured port 1 as a read port, and then you can read whatever data is in port 1, read that data to the accumulator, and then move the same data from accumulator to another register. And the reason you have to write all ones to all port bits is to do with the internal circuitry of the ports. Okay, so remember that all ports, here in this example we showed just for port 1, but for all ports, to read from those ports you have to do this step, write first all ones to all port bits. Okay, this is true for all the ports. Okay, and I will explain you why this is so. So let's first start with port 1 internal circuitry. Okay, so you see, this is the port 1 external pin, and this is the internal side of the port 1. So you have a latch here, okay, and you have this internal pull-up transistor and internal pull-up resistor and the transistor here. Okay, so let's say you have a 1 at the input. Okay, so to make this port as a read port, you have to place all ones on this port. So let's find out the reason. So let me put a 1 here. So this is for one of the pins, and this is true for all the pins. So when you put a 1, the output of the Q of this D latch is 1 and the Q bar is 0. Okay, so when Q bar is 0, this transistor is switched off. Okay, and when this transistor is switched off, this point is connected to VCC, okay, through this pull-up resistor. Okay, this part of the circuit is broken because this transistor is switched off. So now whatever, and this part is connected to the external device, okay, whose status you want to read. So whatever value is put here, that can be directly read from the read pin here. Okay, so let's say if you put a 0 here, then the 0 will be read here. If you put a 1 here, then the 1 will be read here. However, putting a 0 here should be done with a bit of caution, because when 0 is here and VCC is here, so there is a significant potential difference between this point and this point. So there is a chance that this external device will start drawing current from this VCC because it's a 0. So you have to make some arrangement that the external device must sink some current, and if that is possible, then you are fine, you can read the 0 here. Okay, if the external device not able to sink the current, the pin voltage here may rise and it may lead to a possible wrong reading. Okay, So putting a 1 here can be directly read. Putting a 0 here, there might be a problem if the external device cannot sync this current. Okay. So, so this has to be kept in mind. Otherwise, the general arrangement is that to read from this pin, you have to put a 1 here, and then only you can read from this port 1. Okay. So if you now look into the circuits of port 2 and port 3, it also has a similar output circuit, a pull-up resistor and a transistor. A pull-up resistor and a transistor. Okay. And because of this pull-up resistor and transistor, your output circuit for port 2 and port 3, they almost look the same as port 1, and you need to put a 1 to configure them as a read port. Okay. So let's quickly look into this circuit first. So let's say if you put a 1 here, and if your control signal is 0, okay, the control signal has to be 0 to operate it in the general purpose input output mode. Okay. So for port 2 as GPIO, you have to set the control signal to 0. Okay. So if you set your control signal to 0, then this circuit is completed. Okay. If you put your control signal to 1, then this circuit will be completed and it will work as a addressing port. Okay. But for control signal 0, it works as a GPIO. So let's say if your control signal is 0, this circuit is completed, and if you put a 1 here, the output will be 1, output of the D latch will be 1. So here it will be a 1, and since this is a inverter, the input of this transistor will be 0, and the transistor will be switched off. And in this scenario, when the transistor is switched off, this part of the circuit works same as port 1. So whatever is put here in this pin can be read from here. And in this case of port 3 also, you see, when you put a 1 here, the output will be 1 here. Generally the alternate output function has to be 1, okay, for your port 3 to become a GPIO, and if that is the case, then the output of this NAND gate will be 0, and again this transistor will be switched off. And if this transistor is switched off, this part of the circuit behaves in a similar fashion. So whatever you put here, that will be directly read from here. Okay. So port 1, 2 and 3, all they behave almost similarly when they are configured as general purpose input output ports, and you have to put a 1 to make it a read port, and for writing you can just put whatever you want to write on this internal bus, but to read you have to put 1, and then only you can have these ports as your read ports. Okay, so port 1, 2 and 3 are similar in this fashion. Okay, So now let's look into port 0 internal circuit. So port 0 is a little bit different. So already you can notice that instead of the pull-up resistor, you have another transistor here, okay. And since port 0, as you saw earlier in this lecture, that it can be multiplex for both, data and address. So you have this pin or this input here, where depending on your ALE, whether it is 0 or 1, this will contain the data or the address, okay. And your control is usually it is usually 0 when you are using it for a general purpose input output. It is 1 when you are using it as data or address, okay. So so let's say let's focus into the general purpose input output operation of this port 0. So for that your control is 0, okay. So your control is 0, and because your control is 0, this circuit will be closed, okay. So if your control is 0, then this point is connected to this. If your control is 1, then this point is connected to this, okay. So we are focusing on the GPIO characteristics of port 0. So for that your control is 0, okay, and let's imagine that this circuit is completed, okay. So if your control is 0, you can also see that the output of this AND gate is 0, and therefore this transistor is off, okay. Now if you want to use this as a read port, then you put a 1 here, as you do for all the ports, and if you put a 1 here, the Q output will be 1, but the Q bar output will be 0, and since the Q bar output is 0, this will be going here. So here the input of the transistor is 0, so this transistor is also off, okay. So both these transistors are off, so that means this point is floating. It is neither connected to VCC nor to ground, so this point is floating, or in other words, this is a high impedance state, okay. So whatever you put in this pin, which is usually connected to the external devices, that will be read here. So this is for the read operation. And usually if you put a 0 here, then that 0 can be easily read, okay. But if you put a 1 here, because of this floating and high impedance state of this pin, that 1 cannot be properly read, okay. So there has to be some means to pull up this point with some external resistance to VCC for reading a 1, okay. For reading a 0, it's fine, it can read even in this high impedance or floating state, but for reading a 1, this point has to be pulled up. So therefore, while you are using port 0 and you want to read a 1, you have to connect port 0 with some pull-up resistors, okay, some external pull-up resistors, external pull-up, okay. This is different compared to port 0, this is different compared to port 1, 2 or 3, where you had an internal pull up. Okay. So this is what is required. So this is this differentiate port 0 from the other ports, because it doesn't have an internal pull up resistor. You have to connect external pull up resistors to avoid this floating or high impedance state while you are configuring this for read operation. Okay. So for write operation, whatever you put here, that will be written to the external device or wherever this pop-in is connected to. Okay. So this in general is about all the 4 ports and the details of it. I would encourage you to do some external reading about these ports, so get the concepts of these ports a little better. And there are numerous sources from where you can do that. So for example, you can go through different sources in the internet where you can go through the details of these ports. Okay, so I will share this with you later in Brightspace to get some better understanding of the port circuits and their operations. Okay, so so let's move on. Okay, one more thing is remaining. So when you use port 0 as address data multiplex, which is another function of the port 0, then in such a case this control pin, this control signal is 1. Okay, and if and this point is connected to this. Okay, so whatever be the value here in this bus, it can be an address or a data depending on whether your ALE is 1 or 0. Okay, so let's imagine that this point is also 1, whether it is address or data. Okay, so in that case this or let's say, okay, let's imagine that this point is 0. Okay, so in that case the output of this AND gate will be 0 and this transistor is off. And since this is a negative logic here, so here the input of this transistor will be 1. Okay, so this transistor will be on. Okay, and this point will be connected to ground or logic 0. Okay, so you can see if you put a 0 here, whether it's an address bit or a data bit, that can be read here. Okay, through this read pin. Now if you put a 1 here, then here you will get a 0. Okay, and here you will get a 1. Okay, because control signal is already 1. So so if this is 1, then the output of this AND gate will be 1 and this transistor will be on. Okay, and this transistor will be off. So it will be pulled to VCC and you can read a 1 here. Okay, so so let me explain it once more. Okay, so let's get rid of this. Okay, so let's imagine that my address or data, whatever it is, let's say this is 0. Okay, and the control is 1. Okay, so if that is the case, then the output is 0 here because of this AND operation. control 1, this one is 0. So this transistor is off, and here you have a 1 because of this negative logic. This circuit is complete because my control is 1, and we have a 1 here. So this transistor is on, and this point is pulled to ground, so this point is at logic 0. So if your address or data, whatever it is 0, then you can read a 0 from this pin. Okay, and your address or data is 0 based on your ALE pins value. Okay, if your ALE pin is 0, then it is the data that is 0. If your ALE pin is 1, then it's the address that is 0. So whatever is input here, that is read here because of this arrangement. Okay, now let's see the other case. Let's imagine that your address is 1, your control is still 1, so your output of your AND gate will be 1, and this transistor will be on. Okay, this circuit is complete, and here you will get a 0, which will be the input of this transistor. So this transistor will be off, and this point will be pulled to VCC. So this is at a logic 1, and this logic 1 can be read here. Okay, so whatever is the value of this pin, that can be read here, and this pin is data or address based on the fact that ALE is whether it is 0 or 1. Okay, so this is how port 0 can be used as address data multiplex. Okay, so some instruction, when it comes to the ports, some instruction can be read from the contents of the internal port latch instead of reading the status of the external pin. Okay, so some instructions can be read directly from here instead of here. Okay, so for example, when you are doing a logical AND operation denoted by ANL this, so you are basically ANDing the contents of accumulator with port 1, then in that case it reads the internal latch of the port and brings the data into the CPU. The data is ANDed with the contents of A, the result is rewritten back to the port latch. Okay, and then the port pin data is changed and now has the same value as the port latch. Okay, so let's look into single bit addressing. So in many applications we just require the value at one pin on a specific port. So fortunately the 8051 has the capability of accessing specific port pins, and it can set them either low or high. So let's see an example. So you can use this type of operations, set B and clear, to individually access a bit in one of the ports. So for example, if you have to write a code like this, write an assembly program that detects when port 2.5 is non-zero and sends a high to low pulse to port 1.5. So you can use this type of commands. So you set the specific bit 2.5, that is your input. Okay, so you have to configure that by setting it to high, as we discussed so far. If you are reading this particular pin, this has to be first set to high so that you can use it as a read pin, and then you are constantly monitoring the particular pin 2.5. okay, so you are using this jump instruction J and B to monitor this port 2.5. So 2.5 is first configured as an input port by doing this, by setting it to high, and then the 2.5 whatever input is placed there, that has to be read, and the code wants you to detect a non-zero, so that's why it is constantly monitoring using this JNB instruction. So whenever this is 0, it will jump to whenever it is non-zero, it will jump to the next line. If it is 0, then it will stay in the same line, so you have a loop here. It's going to the same line which is labeled as repeat. Okay, so you are staying here, you are looping around this line until it is non-zero. When it is non-zero, it is going to the next line and it sends a high to low pulse to port 1.5. So it's first setting it to high and then clearing it to low. So a high to low pulse like this will be sent to port 1.5. So this is an example where you are using the bit addressing or the bit manipulating capability of the ports. So you can use different instruction for single bit operations. So set B and clear you saw, they can be used to set the bit to 1 and clearing it to 0. You can complement the bit also by using this instruction, and then you can jump based on the status of the bit, whether the bit is 1 or whether the bit is not 1. You can jump based on these two conditions using these two instructions, and then you can also jump if the bit is 1, but while jumping you cleared the bit as well. So JBC is that particular instruction which you can use. Okay, so with that I will stop here for this lecture. I will see you in the next lecture. Thank you.